Welcome to Caltrans LSIT LS Exam Preparation Course. One aid in your preparation for California licensure examinations. A word of caution, don't use this course as your only preparation. Devise and follow a regular schedule of study which begins months before the test. Work many problems in each area, not just those in this course's workbook, but problems from other sources as well. This course is funded by Caltrans, but you and I owe a profound thanks to others, the course's instructors, from the academic community, the private sector, other public agencies, and from Caltrans as well. We wish you well in your study toward becoming a member of California's professional land surveying community.
Hi. Welcome to the world of astronomy. Well, maybe not astronomy. Maybe better said, welcome to the world of astronomic azimuth determination. Astronomy is a subject like that big, and we're only going to talk about maybe that much of it. Only that part that applies to the land surveyor's examination and what you need to know to answer a problem in astronomy. The purpose of this video is to help you answer an astronomy problem in the land surveyor's examination. And all that we're going to talk about is going to be structured toward that end. One thing you want to remember, that in the examination, it is not the examination that's your enemy, it's the clock. The examination is an open book examination. And if you had all the time in the world and you got an open book, hey, you would pass the test, right? And the test, once you pass it, you're going to have your license to survey. So the test is your friend. It's that clock that's your enemy. But you are limited. So again, we're going to structure how we deal with the land surveyor's examination and how we work an astronomy problem doing that. Now, my name's Jack Sands. By the way, Jack's the nickname for John. And I'm going to be your tour guide for this video. Now, I work in the San Diego County Surveyor's Office in the Department of Public Works. Now, in this video, we're going to cover the Bcs Triangle. We're going to talk about how the sun, the earth, and the stars interact. We're going to talk about latitude, longitude, Greenwich hour angle, declination, local hour angle. These are all the things that you need to work the Bcs Triangle. We're going to be doing this using graphics and also a three-dimensional model. Now, the three-dimensional model is going to help you a little better understand this interaction of the Earth and the Sun, where sometimes graphics just doesn't quite get it done. And then we're going to take a recent land surveyor's examination, and we're going to go through it step by step, so you'll see just how an astronomy problem can be worked. As we move through the video, we'll be naming and describing various terms that are associated with astronomy. You're going to find these terms in your workbook in Unit 4, and that unit is titled Azmuth Determination by Celestial Observation. So let's take a look at a Bcs triangle. The Bcs triangle is a spherical triangle, and in a spherical triangle, the parts, the three sides, the three angles are all measured in degrees, minutes, and seconds. Now, the Bcs takes its name from the letters assigned to the three corners. That's P for pole, Z stands for zenith, and the S stands for sun or star. The Bcs triangle can have many shapes. It's dependent on where Z is and where S is. Now, P is the North Pole. It stays where it is. If it doesn't stay where it is, then we got a problem a whole lot bigger than this land surveyor's examination, and that'd be a whole nother ballgame. But it stays where it is. It's the pole, and Z and S move, and that's what changes this shape. The Bcs triangle that you see is a morning observation with the Z, the observer, somewhere in California. You know, it's going to be a California land surveyor's examination, so that's why California. And the S, the sun, is somewhere in the morning because it's coming up. It hasn't got to our meridian yet. The Bcs triangle shown here is on the Earth's surface. The Bcs triangle used to compute the azimuth is on the celestial sphere. The celestial sphere is a sphere of infinite radius with its center at the Earth's center, its north, its south pole at the extension of the Earth's north-south pole, and its equator an extension of the Earth's equator. The sun and the stars are all presumed to be on the surface of this globe regardless of their distance. We will show the Bcs Triangle on the Earth for the sake of understanding a little better its relationship to the Earth. Let's take the display showing the Bcs Triangle and build it one step at a time. All the lines of latitude and longitude need a starting place, an origin. For latitudes we use the equator, and for longitudes we use the line of longitude that runs through Greenwich, England. Latitudes are measured north or south from the equator, and the longitudes are measured either east or west from Greenwich. The reason we use Greenwich, the Greenwich meridian, as the zero meridian is because, hey, the English were here first. They wrote the book. You think they're going to put it in Ireland? No, sir. Now let's add a line of latitude and a line of longitude at Z. Remember that the location of the observer is at Z. And next we're going to add the line of latitude and longitude at S. That's where the line from the sun to the center of the Earth touches the Earth's surface. Now, when we're talking latitude and longitude for the sun, we don't call it latitude and longitude. We call it declination, and we call it Greenwich hour angle. But it's still a measure, declination of latitude, and the Greenwich hour angle a measure of longitude. Now we can put in the legs of our Bcs triangle. P down to Z, P down to S, and Z over to S. And now with a little magic, we can make our triangle shine. Ain't TV wonderful? Now let's add the symbol for west longitude and the symbol for latitude. The angle of longitude measured west from the Greenwich meridian to the longitude of the observer is called west longitude. The symbol for longitude is the Greek letter lambda. Just think of a giraffe going west. The angle measured north or south from the equator to the latitude of the observer is called phi, spelled P-H-I. That's a little circle with a line through it. Next, we're going to put in GHA, declination, and LHA. The angle of longitude measured west from the Greenwich meridian to the longitude of the sun or the star is called Greenwich hour angle. The angle measured north or south from the equator is called declination. The angle of longitude measured west from the longitude of the observer, that's all the way around west on our picture, to the sun is called local hour angle. And the key here is the first word. When we're talking from Greenwich around to the longitude of the sun, in this case, that's Greenwich hour angle. When we're going from the zenith or the local, the place of the observation, we go around west, local's the key, that's local hour angle. Now all that's left to do is identify the parts of the triangle. Let's start with the angles. The angle P, or I should say, the angle at P is called little t, that's small letter t, and it's related to LHA. Whenever LHA is more or less than 180 degrees is how t relates. You can see that in our picture, LHA is very large because it goes all the way around, and what's left is t. So you can see the two together make 360 degrees. Now, this is a morning observation. If this were an afternoon observation, then you could see that the local hour angle would be rather small, and that t and it would be the same thing. So now you can see how the key to t is LHA. When LHA is 180 degrees or less, t is the same thing. When LHA is greater than 180 degrees, then to get t, we subtract LHA from 360. But the nice thing about it is you don't have to worry about that at all, because we just don't use t anymore. Just know that it's there, and that's why we identify it at that part of the triangle. All of our equations now just use LHA. The azimuth angle, that's the angle we're after. So it can be observed, but in this situation, because we're talking about the land surveyor's examination, allow that that's the angle that we're after computing. And then the other one, the one at where the sun is, that's called the Peril Actic angle. And why the Peril Actic angle? Why do we call it that? Hey, you got to call it something. As stated earlier, the sides of the triangle are measured in degrees. The side from P to Z is 90 minus the latitude, colatitude. Co stands for complementary angle. The side from P to S is 90 minus the declination, co-declination, again, complementary angle. The side from Z to S is related to the vertical angle. It can be determined by measuring the vertical angle to the sun, star, or it can be computed from the time. The letter H is used to identify this side, sometimes referred to as the altitude. The side itself is 90 minus H, co-H. Again, complementary angle. And there you have it. The PZS triangle with all of its supporting information. Now that we have developed the PZS triangle, let's find out how it gets started. Let's take a three-dimensional model that we have, which is going to help us a little better understand this, and just show how we can get that PZS triangle. Here is our three-dimensional model. This is the Earth, this is the Sun. Now, contrary to what you've been told, the sun is not this big fiery ball in the sky that we go around. We do go around it, but it's just what you see. I mean, when you look up there and you see the sun, it's a little round ball. That's what you've got, a little round ball sun. I lie. But for the sake of the three-dimensional model, this is what we have to have. Now, another thing that we're going to do here is we're going to, I would like to say pretend we're God, but the Caltrans people say I can't do that on the video. So we're going to be astronauts. And an astronaut, we're going to be up in the, above our solar system as an astronaut, looking down with the idea of what is our perspective. Looking down, as our astronauts, as we as astronauts are doing, everything is counterclockwise. The sun may even turn counterclockwise. We turn counterclockwise. We revolve around the sun counterclockwise. This is 1 year that you're looking at, one complete revolution of the Earth going around the sun. So think of it, everything clockwise. We turn clockwise, we go around the sun clockwise, the sun may even turn clockwise. Now what you're looking at right now is the sun shining on the top part of the Earth, the northern hemisphere. That would be our summer here in California. Right now, because, and then you also see that the pitch of the Earth has maintained itself. That's a pitch of about 23.5 degrees, and that stays that way. Even though we're turning, you can see that that still stays at that pitch. As we move around and get to this position, you can see that the sun will be shining directly at the equator. And because we're going from summer toward winter, that would be what we call the autumnal equinox, or autumn equinox. As we continue on for another 3 months, and we get to where the sun is shining on the lower hemisphere, that would be our winter. That's what we'd call our winter solstice. And then again on around to where, as the sun shines to the equator, coming from winter to summer, it would be the vernal equinox. And then again, 1 year later, the sun shining on the northern hemisphere, back to the summer solstice. Now, we need to build a PZS triangle, and where does it come from and how? Well, first of all, we're going to have a P. P stands for North Pole. Z stands for us. Where are we? Zenith. Where is the observer? Because, again, we're talking about the California Land Surveyors examination. It's going to be in California. So let's just say that right here is California, and that's our Z. Now, an S in the graphics display PZS triangle we saw, how did that get started? It started because we were doing our thing like this in the summertime, and let's just first of all put in Greenwich. Remember we had to have a 0 longitude? Well, here's G for Greenwich. Let's say that Greenwich is right here. Now, when the sun's shining on Greenwich, what is it in Greenwich? Right, noontime. And as we continue on, eventually the sun gets to our zenith. It would be what? Right, it would be our noontime. Let's go back. Let's just say that it's noon at Greenwich, and we're moving along, and all of a sudden, we stop the Earth. Now, astronauts cannot stop the Earth. Only God can stop the Earth. So now, regardless of what Caltrans says, we must pretend we're God. As God, and stopping the Earth, when the sun was shining directly on the Earth toward the center, boom, there was S. And because we stopped it, we created the 3 points of our PZS triangle. P, North Pole, Z, where we made our observation, and S, where we stopped the Earth. Now, naturally, this kept going. But at the time we stopped it, that's where they were. And now you can see the PZS triangle. Let's just take a little piece of thread here. And you can see the triangle, very similar to the one in the graphics. PZS triangle. And that's how we got it. Now, this can have many shapes. The only reason that the shape is this way is because of where Z and where S are. Now, because it's California Land Surveyors examination, and that's what we're working on, we're going to keep Z where it is, and we're going to keep... No, we don't want to change P. When that changes, again, we got a problem that's a whole lot bigger than this examination. So P stays the same, Z stays the same, but let's say that this was an afternoon observation. Let's say that, here we were, say, at Greenwich, moving along, the sun eventually passed our zenith and continued on till, we stopped the Earth again. The line from the sun right to the Earth, boom. Again, we have a very similar triangle, except that now P and Z have reversed themselves. Here's our triangle again. Very similar looking again, except Z and P are on the, I should say, S and Z are on different sides. Let's say that it's a winter observation. Let's come around over here to where we would be in the winter. And again, remember, looking down from the top, everything is counterclockwise. Let's say that the sun starts at Greenwich, and it might be a morning observation again. We stop the Earth, and a line directly from the sun to the Earth would be where S is. But now you can see we're going to have a very long, elongated PZS triangle, because now the sun is below the equator. That would be a minus declination. Remember, when we talk about the latitude of the sun or the star, it's declination, it's not latitude. So this would be a minus declination. And one thing to be thinking about in that examination is when we're talking about declinations, they can be plus or minus. In the little ephemeris book that you'll be probably having a copy of in the Land Surveyors examination, the minus will be shown, the absence of minus is a plus. Don't do that in the examination. In the examination, when it's plus, you write down a plus. When it's minus, write down a minus. And that way, if it was minus and you forgot to write it in and you just figure it was a plus because of the absence of it, you're going to get the wrong answer, and there goes the question. Anyway, you can see how the PZS triangle can have different shapes. Let's go back to the summer, and so that we work with a triangle similar to the one in the graphics, where we had Greenwich, and we finally had a morning observation. The sun was directly shining to the center of the Earth, and our PZS triangle looked like this. Sort of. One other thing I want you to remember or know about is there's a thing called sidereal hour angle, or sidereal time. And what is sidereal time versus solar time, or civil time, sun time? And that is this. Right here we are at our zenith looking directly at the sun. The stars work a little different in this regard, in that the stars are all out here on the celestial sphere. And if you'll see, we have a star. Our star and our sun are on direct line with each other. And remember, everything's counterclockwise. Now let's take one 24-hour civil solar day, and we'll just go around. Now I'm going to exaggerate the movement here so that you can see what we're talking about. Here we are back to, boop, I'm going to stop, and the zenith is looking right back at the star. We've gone 360 degrees to the star, but you can see we have yet to get back to the sun. A little bit more, actually about 4 minutes, and we're back to the sun, and there's 24 hours. So you can see that measured in solar time, the time on your clock, civil time, measured in that time, a sidereal day is less. It's 23 hours and approximately 56 minutes. The solar day, 24 hours. So you can see sidereal time, sidereal hour is a little bit less. One other thing to be aware of is we can do and create a PZS triangle without ever making an observation with an instrument. Because all you have to have is a clock. As soon as you say, "Nope, stop the world," there's your PZS triangle, it's done. But we don't. We have an observation, we have an observer, we have a zenith, and at that exact time, an instrument sighting the sun stopped its motion. Now, things went on, but we had stopped it right here, and at that time, when we were observing the sun, let's allow that we took our instrument and looked to an observation like that. Now we have the PZS triangle, from which we will later see how we can compute this azimuth angle, and having measured an angle to some fixed point on the ground, we can now add the azimuth angle to that angle, and we can have an azimuth to a fixed point. That means we can pick our instrument up and go away and come back at some other time and use the azimuth established on that line. So there you have it. The PZS triangle, where it comes from, and how we do it. Now let's take what we've learned here and go back and apply it to a land surveyor's examination problem. We'll use the problem given in the 1989 California Land Surveyor's examination. It was a 20-point problem. Now 10 points of this were for determining the latitude and longitude at Station Ruck. And 5 points were for computing the azimuth from a line from a solar observation, and then 5 points were for computing the angle of the closure. We're going to deal with only that part that had to do with determining the azimuth from observing the sun. And we will, the problem asks that we use either the hour angle method or the altitude method. And we're going to use the hour angle method. The equation for the hour angle method and the equation for the altitude method are displayed on the screen. They are also given in your workbook. An important consideration at this point is which will take the longer, the hour angle method or the altitude method. Remember, time is the enemy. In today's world of solar observation, the hour angle method is preferred. It is more accurate, it is easier to observe because only the vertical limb is observed. But this ain't the real world, this is the test. And in the test, it's pass or fail, and again, time's your enemy. The altitude method in this problem will take less time because the hour angle method requires we compute LHA and declination. The altitude method needs only the declination, and that's one less thing to do. The other component, H and latitude, the other components, H and latitude, are given. If we had to correct H for refraction and parallax, then it might be a trade-off. You're going to have to decide which is going to take the least amount of time. In this problem, the altitude method would be the one to use because H is given corrected for refraction and parallax. Now, after all of that, why are we using the hour angle method? So that you'll get an instruction in how to compute LHA. The equation for the hour angle method requires that we know LHA of the sun, the declination of the sun, and the latitude of the observer. So let's develop these items one at a time and then put them together into the equation. To compute the LHA, we need to know the time of the observation. Not just any time. We need Coordinated Universal Time, UTC, sometimes called Greenwich time. UTC is then corrected to get the base time on the actual rotation of the Earth. This correction is called DUT, and the DUT correction is given in the problem. This corrected time we then call UT1. The reason we need UT1 is because the ephemeris data is for UTC. So here we go. To get LHA, we first must convert the Pacific Daylight Saving Time, Pacific Daylight Saving Time, to UT1. The display shows a way to deal with the information given to arrive at UT1. The display shows a way to deal with the information. Most LS problems of this type can be answered in this style of format. We list all the necessary information and then deal with it algebraically as a group. It can be done each one by itself, but it's probably a little better that we deal with it as a group. First, the time, 5:23:35. Now, the reason we know this is PM, because we're going to add a PM correction, is because of the picture that you're going to have to look at in your workbook of the problem. They didn't tell us this was PM. Now, whether that's deliberate or not, we don't know. We do know that it's PM by just observing that the sun was observed in the afternoon. The PM correction, 12 hours. Now the correction for time zone, 7 hours. Why 7 hours? Trust me. When it's Pacific Daylight Saving Time, you add 7 hours to get to UTC. When it's Pacific Standard Time, you add 8 hours. Fortunes have been won and lost betting on whether you add or subtract, spring back, fall ahead. I don't even remember the little jargons. Just allow that with this problem, it's Pacific Daylight Saving Time, and we're going to add 7 hours. Next, we put down the watch correction. Now, when you've got a fast watch, you subtract the correction. This we subtract because the watch is fast. Why do we subtract the fast watch? For the same reason that we add a slow watch, because SAN says so. You can figure it out for yourself later. Right now, let's just trust Jack. Our last correction is the DUT correction. This is given in the problem. It's a minus 0.5 seconds. This is the correction needed to change that UTC to UT1. Now we will take the time of the observation, 5:23, and add all these corrections algebraically. The result is UT1. As you can see, we have more than 24 hours at UT1, 24, 23, 34, 2. And you can almost bet that any astronomy problem that you get of this type in the examination, they're going to do this. It's going to go over 24 hours because they want to know that you know what to do with it, that you have to go into the next day when you're looking into the ephemeris information. Now we can compute GHA. The ephemeris will give us the GHA for 0 hours on the day of observation. We have just previously determined that the UT1 of the observation, we have just previously determined the UT1 of observation. The GHA of the observation is the GHA at 0 hours, plus the amount of GHA for the elapsed time from 0 hours to UT1. To compute GHA for the elapsed time, we need to first compute the total amount of GHA for the day of observation. We do this by taking the difference between the GHA for 0 hours today, that's the 180, 50, 58.4, and the GHA for 0 hours tomorrow, the 180, 52.033. And then we add 360. And the reason we have to add 360 is because there was a change in the elapsed time, but it took a whole 24-hour period for it to happen, and that's a 360-degree addition. The result can be more or less, depending on whether the GHA at the beginning of the day and the end of the day, if you will, the next day, was more or less. We then multiply this total GHA for the day by the UT1 divided by 24 to get the GHA for the elapsed time. If this all sounds very complicated, well, welcome to the club. As you do it, it will start to make sense. Each day must be considered separately because the total amount of GHA changes from day to day. Here we might want to talk a little bit about equation of time. Fortunately, you don't have to worry about it anymore because all the ephemeris data is in GHA. But the equation of time is that because the sun does not travel, the Earth as it travels around the sun, does not travel at a constant speed. It has a speeding up and a slowing down. And this causes the real sun, what they call the apparent sun. Let's just talk about noontime. At noon, on our clock, it may say noon, but when you look up, the sun may not be right on the meridian. It may be before, it may be after, because of the speeding up or slowing down. And that's what the equation of time is all about. It can be very confusing, very complicated, and again, fortunately, you don't have to worry about it, because your ephemeris tables will take care of this for you. The GHA corrects for that. And with our problem, adding all this up together, the GHA for the elapsed time is 523.34.1. And then we add this to the 0 hours, and this gives us the GHA at the time of observation, 186.44.32.5. Now we can compute the LHA. The formula, LHA equals GHA minus west longitude, you can find in your little ephemeris Leach tables, which is a real good little study text that also has the ephemeris in it. 119.46.54.5. And now we've got the first part of our problem. Subtracting that, we get LHA 66.57.38.0. Now, let's do the declination. Computing the declination, you're going to find, is a lot similar to what we did when we computed GHA. Different numbers, but generally the same procedure.
We take the difference between the declination for 0 hours today, 16:32:17.5, and the declination for 0 hours tomorrow, 16:48:59.7. Multiply this by UT1 divided by 24. Add the answer to the declination for 0 hours today. Sound familiar? The declination for the time of observation ends up being 16:32:33.9. As you can see, the procedure is very similar to that for getting GHA.
One thing I might bring to your attention here is that there is a correction to the declination that this problem didn't address. And it can be as much as 3 or 3.4 seconds. The problem didn't ask for it, so you're not going to have to worry about it. But if it did give you a declination correction, you'd want to, or they'd want you to attend to it, you'll find there's an equation for this in your little, again, the little Leach ephemeris tables. Because our UT1 was so close to 0 hours, the correction would be 0. This problem did not supply this correction and did not require it, but it's a good thing to know about it. The formula for computing this, again, is found in your little Leach ephemeris handbook. Now, the last of our 3 items that we need for this equation is the latitude, and that's a given. That's 36.48.57. If you'd worked the first part of this problem, that's where that would have come from, but we're not dealing with that. Now let's take these 3 factors that we've been able to put together, and let's put them into the equation and solve. The equation shown on the screen is also given in your workbook in Unit 4. This is the hour angle equation. So go ahead, work the equation. You can stop the video while you work the equation. Well, how did you do? If you had to work the equation about 6 times to get the answer, then you're par for the course. The good thing is that it isn't for the gold. You're just practicing for the real thing. You probably made dumb mistakes like, 2 + 2 is 5. You didn't change the degrees, minutes, and seconds to decimals of a degree. Most mistakes are because you're in a hurry. And you will be in the exam. Remember, time is your enemy there. But the more you practice and the more in control you will be, I know you're always hearing this, practice, 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 but it's true. Be prepared and you're going to pass that test. I can just about guarantee it. The answer to our equation is minus 89.47.48.2. When you have the answer to the equation, you will need to do a normalization so that the result will reflect the azimuth reckoned from north, goes clockwise, I guess for you that would be this way, and is positive and less than 360. Use the box in the display to normalize the answer. This box is also given in your workbook. The LHA is between 0 and 180 in our problem. and the answer to the equation was minus, that means that we have to add 360, and then that makes our answer, the azimuth to the center of the sun, 270, 12, 11.8. However, we did not cite the center of the sun. Remember, we cited the left edge of the sun. To compute the azimuth to the edge of the sun, we need to compute what we call the DH correction, sometimes DZ correction. We're going to say DH. And the formula for DH is the DH equals the semi-diameter divided by the cosine of H. If the left edge is sighted, the correction is subtracted, and if the right edge is sighted, then we would add it. Why? Yeah, you guessed it, because Jack says so. If you draw a picture, you'll see why it is so. Why can't we just use the semi-diameter without dividing by the cosine of H? Good question. It's because as the sun moves in relation to the local meridian, the spherical triangle changes its shape. This changes the size of the DH correction angle. It's not important that you understand this. It is important that you know about it. In our problem, the semi-diameter, which is 1552.7, and the H, which is 280549, are given. The semi-diameter changes very little in a 24-hour period, only 0.2 of a second. And because our observation was so close to 0 hours, we will use 1552.7. H is the vertical angle corrected for parallax and refraction. It can also be computed if LHA and latitude and declination are known. But that takes time, and time, again, we don't have. So we'll just use H given. The computed DH is 18 minutes. And because the left edge was sighted, we're going to subtract. The azimuth to the left edge is 269, 54, 11.8. Now let's take a look at the display and start at the top and compute each factor. First, we take the computed azimuth, the 270, 12, 11.8, then subtract the DH correction, the 18 minutes. This gives us the azimuth to the left edge of the sun, 269, 54, 11.8.
From this, we subtract the angle measured at station Ruck from the left edge of the sun to station Rots, 187, 30, 56. This angle is given in the problem. All this results in the astronomic azimuth from Ruck to Rots, 82, 23, 16. And that's our answer. We're done. And you thought this was going to be hard. The rest of this particular problem asks that we compute the angle of closure at Ruck. But this is not an astronomy question. That's getting into the conversion of astronomic azimuth to geodetic azimuth and then converting to geodetic azimuth. Or excuse me, to grid azimuth. This will be covered in the video dealing with the California coordinate system. In the what it's worth department, that answer is 15 seconds. We all know that a picture is worth 1,000 words, so let's take a picture and see, just go through this again. Now, north in the picture is true north or astronomic north. And the reason it's astronomic north is because we just solved the Bcs Triangle, which is an astronomic triangle. The P in the triangle is the North Pole. You can see where we had the azimuth to the center of the sun that was computed from the equation, 270, 12, 11.8. Our little correction of 18 gave us that azimuth to the edge, the leading edge or the left edge of the sun, 269, 54, 11.8. We then subtract the angle measured at station Ruck from the left edge of the sun to station Rots. Again, this is the angle given in the problem, 187, 30, 56. And that gives us the azimuth from Ruck to Rots, 82, 23, 16.
Now, if this were a Polaris problem, we'd deal with it just the same way. You could use the same equation. Everything would be the same, except you would not have to compute the DH correction for obvious reasons. You wouldn't have to be sighting the left edge of the star. The equation shown on the screen can be used for computing the azimuth, when you cite Polaris. This equation is a little simpler. This equation is also given in your workbook. This equation should not be used for the sun or other stars. It works for Polaris because Polaris is so close to the North Pole, less than a degree. In the equation, h is needed. If h is not given, you would be better off using the hour angle equation because the time it would take to compute h would be more time than just working the hour angle equation. The computed azimuth using the Polaris equation is small, either east or west of north. It is east of north when the LHA is between 180 and 360. It is west of north when LHA is between 0 and 180. When it is west of north and the azimuth is reckoned from north in a clockwise direction, well, that'd be like this for you, it must be subtracted from 360. What we've covered so far is the kind of problem more than not in the land surveyor's examination on astronomy. There are times when you're going to get what I'll call a word problem. You should burn a candle that you get one of these. Offer your firstborn to the goddess of examination questions. I call these gimmies. These kinds of problems do not take time. They can be answered without time-consuming computations. Remember that time is your enemy. Let's take a look at a gimme problem. Go to Unit 4 in your workbook and find problem B3 from the 1988 California Land Surveyors examination. This problem is a 10-point problem. That means in this examination you were given 48 minutes to work this problem. Measure that against the time it would take to work the solar problem we just did. That was only 5 points. This problem has 17 questions, 15 true or false, 2 multiple choice. If you did nothing more than guess, the probabilities are that you could get half of them right, and that would be 5 points and maybe 5 minutes, leaving you as much as 43 minutes to work on another problem. Now you can see why I call these friendly problems. You're in an open book examination. If you just search for the answers, you should be able to get maybe 7 or 8 points in 20 minutes. Maybe you should offer not only your firstborn, but your spouse also that you get one of these. Let's take the questions one at a time. The problem states that if the question is false, you should give a brief explanation, and the key word there is brief. Don't spend a lot of time. So let's start right out. Number 1, astronomic azimuth is based on true north. True. Nothing else to do. Number 2, grid azimuth is based on true north. Well, we just said no to that, so it's false, and we can say see number 1 for a statement. Geodetic azimuth is astronomic azimuth minus mapping angle plus second term. I don't know, and I'm the expert. You go to a book and you find a formula, and you'll find this formula in a publication 253. Remember, you've got an open book exam, and you've brought every book you own to this thing, so just look it up. And you're going to find that the correct is grid azimuth equals geodetic azimuth minus mapping angle plus second term. Number 4, to determine true north from observations on Polaris, the latitude of the observer must be known. No, false. Look at the Polaris equation. There's no latitude in there. And again, because you're going to be making just a brief statement, just write it down. See Polaris equation and then maybe show the Polaris equation with no latitude in it. Number 5, GHA equals LHA minus west longitude. Well, we've just gone through this, but again, you don't try to remember equations. Go to your little ephemeris book, and there it is. LHA equals GHA minus west longitude. So you could say false and nothing more than just write the equation down. On to number 6. The best time to observe the sun to determine azimuth using the altitude method is 1/2 hour after sunrise or 1/2 hour before sunset. No. False. Because when you're looking at the altitude method and you're measuring vertical angle, you're going to find refraction is just too much to deal with. But again, in the test, you're just going to make a brief statement. You're going to say false, too much refraction. Period. Number 7. Exact time is more important when using the hour angle method. This is true. Period. Nothing else to say. Number 8. The hour angle method requires both horizontal and vertical observations to be determined, to determine the azimuth. No, we only have to look at just the vertical observation. So you're going to say false, horizontal only. Number 9. It is not necessary to know the latitude of the observer when using the hour angle method. False. See the hour angle equation. Just write it down. See? We're flowing right through. We're halfway through this, and I'll bet we haven't spent even talking about it more than 3 or 4 minutes. Number 10. I think we just did number 10. No, let's do it anyway, even if we didn't. The best time to observe the sun for determining azimuth using the hour angle method is just after sunrise or just before sunset. That's true, because you're going to have the sun lower in the sky, and the lower the better with the hour angle method. Again, I'm just kind of telling you why, but all you got to do is write true and get on to number 11. Standard time must be converted to local time to determine Greenwich time. False. Again, don't try to remember equations. Just go into the book and find it. And we're going to say that the Greenwich time equals standard time plus, in this case, for California, be 8 hours, depending on what time zone you're in. And here we're in the Pacific Standard Time Zone. Number 12. Local time is increased in California by 8 hours to determine Greenwich time. No. It's the standard time, not the local time. And again, you could just write out the little equation for that. 13. True solar time is local civil time minus the equation of time. Now again, there's that pesky old equation of time, which again, we don't have to worry about because our ephemeris tables take care of it. But here, they're asking us about it. So what do? Again, you don't remember formulas. Go right to that little Leit's Ephemeris Handbook, and you'll find about maybe the third column over, it'll talk, right at the top, it'll tell you the little equation for the equation of time. And just copy it down. 14. A level line at sea level is parallel with a level line at 8,000 feet. Now, what the heck that's got to do with astronomy, I don't know, but it's here. You know, you've got to answer it. And I'm just going to say false, and I'll just tell you that because you're out there further and centrifugal force is working harder on it, you're going to have more of an elliptical path than you would at the sea level, so it's not going to be parallel. And that's about as much as you'd want to say about that. In fact, it doesn't even belong in there, but again, what are you going to do about it? 15. One sidereal day is longer than one solar day measured in civil time. Remember our three-dimensional model when we were looking at the star? And we could come all the way around, and we would face the star a little bit before the end of the solar day. So we know that the solar day is shorter. That the sidereal day is shorter, the solar day longer. So number 15 would be false. Sidereal day is 23 hours, 56 minutes. And then we got 2 more to go, and I'll bet we still haven't used 7 or 8 minutes. And again, right here, let's say you take a hat pin and you just pick A, B, C, or D. Maybe your chances aren't as great with true or false, but you could do it. But let's go ahead and go through them anyway. At what time will the effect of a small error in the determination of the observer's latitude be minimized when making azimuth observations on Polaris? I will peek at the answer, and it says C. C. The Polaris is at culmination. Okay, just allow that at culmination, you're right on line with the star. So it wouldn't matter if you're way down here or way up here. It ain't going to change the azimuth any. So naturally, at culmination would be the answer. Moving right on to the last one, number 17. At what time will the effect of a small error in the determination of the time of the of the observation be minimized when making azimuth observations on Polaris? Well, again, this would be because when the star, which is making its circle, and I may be showing it wrong, it's, I'm looking at you, you're looking at me, just allow it's going around in a circle. When it's at the outer edges, it appears to be only moving vertically, and time is not very critical. So elongation would be the answer. Let's see if I got that right. Number 17 says B. Ha-ha, look at that. Polaris at elongation. And we're done. We've used up, I doubt if we've used up 10 minutes, and again, there's 43 minutes to work another problem. Well, that covers the kind of problems that you're going to get in this LS examination. There are going to either be a problem, you're going to have to work out some numbers that you hope you don't get, or a word problem like you say you're going to be praying to get. And let me add just a little bit more on how to maybe approach the examination, whether it be astronomy or other questions. Again, remembering that time is your enemy. Take the examination when it's given to you, open it up, look at the first question, and say, hey, do I know this? Is the time fair? Let's say you look at the first one and you say, I don't even know what they're talking about. Go right on to the second one. It doesn't matter about time. The second problem you look at, and this is, hey, I know how to answer this, but it'll probably take me a day and a half to do it. Go right on to the next one. Put little check marks by these problems that you're not going to work. Number 3, it's a problem you know, and you say, hey, the time is about fair. I think I can do this. Work problem number 3. Problem number 4, same thing. I don't know what it is. Problem number 5, hey, again, time's fair. I know how to work it. I work problem number 5. You can see what I'm getting at here. I'm working the problems that I'm going to get the best points from. I can go through the whole examination like this, and I may end up only working, let's say it's a 10 problem exam, and I've only worked 6 of them. I go right back to the beginning again, and number 1, don't know how to work it, don't bother with it. On to number 2, okay, again, I know how to work it, but it takes too much time. I don't work this one because I remember one in the back was the same thing, except I could work it. The time wasn't quite as bad. I go back and I work that problem. Let's say I go through the whole examination like this, and I end up only maybe answering 8 of the 10 problems. But I picked the best 8. The 2 that I didn't work are 2 I shouldn't have been working with anyway, spinning my wheels, where I could have been getting good points. So you see what I'm talking about. You want to enhance your chances of getting the best chance of working the problems that are going to give you the best points. Now, there's no magic, but the better prepared you are, and again, I know that's been beat to death, but it's a fact, the better prepared you are, the more selective you are about the problems you work first, the more you enhance your chances of getting a passing score. So, guys, gals, good luck and break a leg.